started the second part of the morning session. The Eve is going to talk about the star formation feedback and self-regulation. And without further ado,
Okay.
Let's get started.
Thanks. Great. So it's a good thing that we had Roman talk about the numerical methods in detail, because I will be discussing results that use these numerical methods for things like radiation hydrodynamics, but I won't be talking about the methods in detail. I will mention, as I get to kind of the things that I use, which of the methods that he talked about that go into this. Okay, so in the previous two lectures, you'll recall that I gave an overview of the interstellar medium, and I also discussed how molecular gas is related to star formation and the detailed processes of star formation. And what I'll talk about today is focusing on, let's see if my mouse is anywhere. Okay, so I'll be talking about the effects that stars have on their environment, that goes under the heading of feedback, and how that, in fact, helps to regulate future star formation, that back reaction. Sorry? This is this square, so this is M83. Oh, yeah, so this whole galaxy is probably, I don't know, maybe 15 kiloparsecs. Oh, this is this square here, so it's several kiloparsecs, yeah. So these are individual H2 regions, but on a larger scale. So you're seeing the effects of the ionizing radiation over a scale that really extends beyond the H2 region itself. Okay, so so here is kind of two of the equations that Roman showed you. One being the equation of mass conservation, and the other the momentum equation. And so there are other equations. So this is only 2 out of 7 of even the simplest equations. So I didn't write down here the energy equation. I didn't write down Faraday's law of induction. And I didn't write down the energy and momentum equations for radiation and cosmic rays. So this is only a small set of the equations that actually would go into kind of even into a treatment that includes sort of everything that can affect the feedback. But this is sort of showing you the terms that go into the momentum equation. So there are gas pressure forces, there are cosmic ray pressure forces, there are radiation forces, which depend on the flux, and there are magnetic forces. So some of these forces, if you think about their effects on, in terms of star formation is a process of compressing gas, but also dispersing gas when you get to the feedback. So some of these forces are kind of one way. Gravity is kind of one way. Others are sort of a double-edged sword in the sense that, for example, for shear, that the term here, I guess this term here can involve shear, which tends to tear apart dense regions, but there can also be compression, so there can also be turbulent pressure compressing gas. So that's just something to keep in mind, is that they look innocent, but they can really do a lot. The other thing to keep in mind is that all of these here, so all of these source terms, the thermal pressure, the cosmic ray pressure, the radiation force, the Reynolds term, and the magnetic term, all of those are subject to dissipation. So thermal pressure, thermal energy is cooled away. Cosmic rays stream and diffuse out of the galaxy. Radiation is absorbed and then it is downgraded to IR and then essentially can leave a galaxy. There's a turbulent cascade, which then ends in shocks, which then end in thermal energy, which then can be radiated away. Magnetic fields magnetic fields can reconnect, and they can also, so all of these have dissipation, all of these terms have corresponding dissipation. And so all of the losses, in a sense, have to be made up for by gains. And that's kind of what we look to for feedback. So if there weren't any feedback, just think about the turbulence and the thermal energy, those are the simplest. If there were no feedback, you would have the turbulence would dissipate, turn into thermal energy. That thermal energy would be radiated, and the ISM would all collapse into dense clouds. And then within those dense clouds, they would further collapse and make stars. So that would be the end. We would have very boring galaxies if there were no feedback. But of course, we know there's feedback, so you can see, you can see all kinds of beautiful feedback in these images here. So what are this? Here I've summarized some of the important different forms of feedback. So there's radiative heating. So that includes both the far UV, which produces the photoelectric effect that I talked about in the heating of the neutral ISM. There is radiative heating, which again of non-ionizing photons that heats dust. And in very dense regions, the warm dust colliding with gas can actually transfer energy to the gas, and that can actually heat the gas as well. But you have to be at quite high density for that to be an important source. Then there's ionizing radiation. And that ionizing radiation, since in general there will be an excess energy of the electrons that are ionized, those will be shared with the rest of the ionized electrons and protons, and so that will heat H2 regions. Some of the radiation, a significant fraction of the radiation, escapes from H2 regions, so that can heat the diffuse gas within galaxies. So in addition to those heating processes from radiation, there are also direct radiation forces, and Roman mentioned this in that source term in the momentum equation, that rho times kappa times the radiation flux. That's the source term, which produces a force in a force on the gas. So that can be so essentially. There's direct far UV. Those photons are absorbed by dust, and then gas particles collide with, whether it's molecules or atoms, collide with the dust, and there's an exchange of momentum that then accelerates the gas. I don't see Phil Hopkins here, but so he's been working on, and he talked about yesterday, how interactions between the dust and the gas may actually involve instabilities in making that transfer of that exchange of momentum. So in addition, the ionizing radiation can be absorbed by when those photons are absorbed by atoms, that actually transfers momentum as well as energy. And then the infrared radiation also has a force that's associated with it. This is more important, of course, in regions where that are actually opaque to infrared, so very high density and surface density regions. So then there's also stellar winds. So these stellar winds are likely to be more important in the environment right around massive stars. I'll mention a little bit more about this in a minute. Then there are supernovae. So supernovae can be either from isolated, so there are type 1 supernovae. There are also runaway O stars, which they're basically ejected at high velocity from star-forming systems, and so then they can be anywhere since they are at very high velocity. But since most stars form in clusters, most of the O and B stars will be correlated with each other, so that clustering leads to superbubbles. And I mentioned that briefly yesterday. So these supernovae, the supernovae produce both shock heating and gas acceleration, because this hot gas is heated, but that very overpressured gas expands and does PDV work on the surrounding environment. So that's an acceleration of of not only itself, but the surrounding gas. And finally, cosmic rays, which are actually created in supernova remnants. They are important in heating, as I talked about on Monday, I think. They're important in heating the shielded gas, and they may also be important in creating large-scale pressure gradients. One thing to keep in mind is the cosmic ray scale height is much larger than the scale height of the cooler forms of the gas. And so the cosmic ray pressure gradients are likely applied over relatively large scales. And I just mentioned here at the bottom a few recent reviews that cover the different forms of feedback. So this is just some kind of general principles to keep in mind related to feedback. I think I mentioned these as I went through. So I wanted to say a little bit more about stellar winds. So the stellar winds were originally thought to be quite important as a feedback mechanism, but observations seem to suggest that they may not be as important as originally thought. In particular, from some recent studies, there's suggestion that there's less than about 1% of the expected X-ray radiation that you would think would be present from a shocked stellar wind in star-forming regions. So that's this paper by Rosen et al. And so where did the energy go? Well, one possibility is that hot gas produced in the shock wind mixed with cooler gas and then radiated away, so you're not seeing X-rays. Another possibility is that the hot shocked gas just escaped from the star-forming system. So it's not well understood yet what is, where did that wind energy go? But there does not seem to be as much evidence for it as originally thought. Okay. So the basic concept of self-regulation, so those were the feedback elements in a sense. Then on the other hand, so what do those elements do? So the basic concept of self-regulation is that when some gas is collapsing and it's making some stars, but these stars, the massive stars anyway, inject energy, and that energy then can, in a secondary sense, that they inject energy and momentum to their surroundings. That changes the state of the gas. That is, it can change it from being neutral to ionized, or or dissociate molecules. That also accelerates the gas. So the feedback actually changes the state of the gas in important ways. The other thing to keep in mind about this is that if you think about the timescales, high-mass stars are generally short-lived. So, they live the highest mass stars live for only, about 3 million years. And essentially all of the massive stars that have important feedback from them only live some tens of millions of years. So unlike our own sun, which will live for many gigayears. So that means because these massive stars inject their energy relatively quickly after star formation, that means that there's a correlation in time. So this correlation in time means that when their stars start to form, their feedback can actually prevent future star formation. So the star formation now is limiting star formation in the future. Okay, so one very basic question is what would limit the star formation in an individual giant molecular cloud? If we look at something like the Orion cloud, what limits how many stars will form out of the gas that we see now? So that's one, so I'll talk about those issues. So star formation feedback at the scale of individual molecular clouds. And this is something that I showed you before, the observed efficiencies in individual molecular clouds, which range from, down here up to maybe 50%. So there's a wide range of observed efficiencies. And of course, that is telling you something about the evolution of star formation. Down here, we don't think that's going to be the final star formation efficiency. These presumably are very young clouds down here. And I should also say that there are some issues about how do you associate star formation with a given cloud, because the stars may be at later stages, they may be more distant from the cloud that they formed in. So there can be issues about associating these, especially in the Milky Way, where you don't know the distances of anything very well. So there are issues in creating plots like this. There are very strong observational issues just in creating that kind of plot. Okay, so then on larger scales, rather than just thinking about an individual GMC, we can think about a whole galaxy on kiloparsec or even galactic scales. And then how does feedback regulate star formation rates over large scales and long time scales? And I'll talk about that as well. And this is the familiar Kennicutt-Schmidt law on the on the left. This is a global version of it. This is a local version of it. This is relating star formation rate per unit area to the gas mass per unit area. And as I mentioned, I think I mentioned this before, but if I didn't mention it before, what you can see here is that the depletion time, which is just the ratio of the gas mass to the star formation rate, that's shortest in the high surface density regions, where the dynamical times are shortest. And I should say, so something that I want to clarify is when we talk about the depletion time, that you shouldn't think of that as a cloud which is just sitting around for a gigayear until it uses up its stars. This is really just a way to characterize the star formation rate per unit gas mass. So don't think of it as actually just slow draining of material into stars. It's really much more evolutionary than that, or much more dynamic than that. Okay, so of course, star formation is important. The feedback is important to the properties of the ISM as well. So really, as I'll be arguing, we need to think about the star-forming ISM as a single self-consistent ecosystem. The star formation is an inherent part of how we understand the interstellar medium. So let me now start with discussion of how feedback works in individual giant molecular clouds. And this is the 30 Doradus region, which is not in our own galaxy, but it's in the LMC. So this is one of the most vigorous star-forming regions in our local part of the universe. This is R136, where it's only a few million years old, but there's about 1 million or several million, I think, young stars there. So this is very vigorous star formation, even in our own part of the, even in our old galaxy. So this is something that I think you will all know, and so I wanted to start with this. So something that's familiar to everyone is, what does a luminous star do to its immediate environment? And the first thing it does is it creates a Stromgren sphere. And a Stromgren sphere is just the ionized region surrounding a luminous UV-emitting star. So this should be pretty familiar to you. So you calculate, in this idealized Stromgren sphere, the recombination rate has to balance the ionization rate in the interior of a Stromgren sphere. So this Q is the number of UV ionizing photons per unit time. So you balance the ionization rate against this recombination rate. And at early times, you just say, you turn this star on, and the density is whatever it was before. So there's some density in the cloud, and then you can calculate the Stromgren radius based on what that initial density was, and the ionizing flux, and the recombination rate. But since this is, in general, you've raised the temperature from 10 degrees to 10,000 degrees, so it's very overpressured. This will immediately start to expand. And at later times, the appropriate density in the interior here will not be the original density of the cloud. It will be something much lower. So you can turn this around and then say, when the ionization front has a certain radius, what is the density in the interior? Just again, you're still balancing ionization with recombination, but now you're asking what's the density in order to get a certain to have the ionization front at a certain distance. So if you then use this ionized gas density, there will be a force on the edge of this. There will be a force applied on the edge of that ionized sphere, this idealized sphere. And that's just from the area of the sphere times the total pressure. And the scaling of that, so the temperature is always about 10,000 degrees, but this scales as the 1/2 power of the ionization rate and of the size scale of the H2 region. So this is telling you that as the H2 region expands, it actually applies a larger and larger force to its environment, which is kind of an interesting effect. Okay, so in addition to that gas pressure force, there's also a radiation pressure force. And you can start by just thinking about, a given Stromgren sphere, which is spherical. But now we will allow it to actually have interior structure. And this is a problem that was solved by Drain a few years ago, remarkably only a few years ago. It's kind of remarkable that this solution was not previously known. But if you look at the requirement for force balance everywhere within the H2 region. This is the equation that you have. So basically, you want to have a radiation force plus gas pressure force is everywhere 0. This first term here is the force on dust from both non-ionizing and ionizing photons. The second term is the force from ionizing photons being absorbed. And then this term is the gas pressure gradient force. So so what's shown here is the profiles of the, so these dashed ones are the, that's showing the radiation pressure, and then the solid curves are showing the gas pressure. And you can see that as you turn up the radiation field, so this is a very, this is a relatively low, so I can't read Q there, but Q is, what's Q? Q is, can't read it. Yeah, so in units, it's probably 10 to the 49. So at a low value of Q here, it's, the traditional uniform Stromgren sphere with a uniform density, very low radiation pressure. But as you turn that up, then the gas actually gets pushed to the outside, and radiation is filling the center. So essentially, you have radiation pressure on the inside, and gas, all of the gas gets pushed out to the outer part. And this is for a very strong radiation field. You just have pushed all of the gas out to the outer edge. So you've really increased you've increased the ionized gas density in the outer parts by filling the interior with very strong radiation pressure. And what's shown in the bottom here is the force relative to the radiation pressure force, which is just luminosity over c, because photons, if you take photon energy and divide it by c, that's the photon momentum. So a force is L over c is the radiation force. So if you compare the forces to c, what's shown here is that horizontal line is, of course, just the total radiation force that you expect to get. What's shown here, that diagonal line is the essentially what I wrote down here. Oops, wrong one. So that's essentially this, the gas pressure force that you would get for a given size, ionized region, and a given photon, ionizing photon input rate. So that's basically that goes as the 1/2 power. And then what's shown in the curve here is the exact solution and the solution that you get just by summing those. And you can see that it's actually quite close to, if you just take the sum of those, the total force is very close to just taking the sum of those. If you actually, integrate that equation, it's very close to that. So you can define a characteristic radius, and this is discussed in Krumholtz and Matzner, where the radiation force exceeds the gas pressure force if the size of the H2 region is smaller than that, and the gas pressure force exceeds the radiation force if it's larger than that. And this characteristic radius is proportional to the input ionizing photon rate. So this gives you an idea of the scale here. If you have just one O star, it's not very big, but if you have a whole cluster, it can be a significant, that size can be not so small. Okay, so if you use that solution, the H2 region, that spherical solution, the H2 region will expand, and this is showing a comparison of, this is showing how the H2 region expands. The gas pressure is low in the interior, as I mentioned, and then there's a shell, which is the compressed gas. This is just showing the comparison between the numerical and between the numerical solution of integrating the full equations and integrating this ODE, which is basically, kind of an approximation because it's not treating the interior structure of this H2 region. It's just using this approximation to the total forces that are applied. And just to kind of see what's going on here, that's the approximate radiation force as applied to the shell on the outside. This is the gas pressure force. But in that gas pressure force, you can use the ionization equilibrium in the interior to compute an approximate value for that gas pressure force there. And you can see that this one, as the ionization front expands, this term will become more important. At small scales, this term is more important. So R goes to 0, this term is 0. But as R gets larger, once you get larger than the characteristic radius, this term dominates. Okay, and of course, if you want to, use an H2 region to destroy a cloud, these terms better end up being more important than gravity. Okay, so what's the criterion for disruption? Well, you've disrupted a cloud if you've essentially accelerated the material enough that that it's moving faster than the escape speed. Or one way to think of it is there are different criteria you could use for disruption. One would be that these forces would exceed this force. Another would be that you've achieved a velocity that exceeds the escape speed. So you could use different criteria for when you have reached disruption. This shows if you're in the regime down here, you can ask, well, what total luminosity do I need? Translating that into ionizing photons, what total luminosity do I need in order to disrupt a cloud? That's a pretty well-defined question. And you can then translate that into a star formation efficiency within the cloud that you need to disrupt the cloud. And what's shown here is in the two limits of totally radiation pressure dominated or totally gas pressure dominated. In the radiation pressure dominated limit, the star formation efficiency would increase as the square of the gas average surface density in the cloud, and inversely with the ratio of the light to mass ratio in the cloud. In the case where it's totally dominated by gas pressure, that is weaker radiation fields, or generally the lower surface density limit, then the star formation efficiency then has a somewhat different scaling on the cloud properties. So these are kind of estimates that you might make for what do you need to destroy a cloud. What does an H2 region need to destroy a cloud? And from integrating that equation, this just shows for a given cloud, using different criteria for disruption, what the efficiency would be. So you can see that depending on what criterion you decide to use, you would have a somewhat different efficiency. But these are the kind of required range of efficiencies. So this is, at typical molecular clouds in the Milky Way, this would be an efficiency between 1% and 10%. And what's shown over here is this green band is below the green band. Evolution is always dominated by gas pressure. Above the green band, evolution is always dominated by radiation pressure. And here, there's kind of a transition between them. And again, for Milky Way kind of clouds, which are in this range here, and surface density is typically of about 100, you'd get a predicted star formation efficiency based on H2 region disruption of between 1% and 10%. So let me say a little bit more about to give you a more intuitive feeling for what goes into these efficiencies. So let's look at the radiation pressure force. So that's L over C, and that, let's see if I have that. So L over C, that luminosity you can write as some light to mass ratio times the mass, so that's m star, where that psi is on the order of 1,000 solar luminosities per solar mass. So you can see, first of all, that low mass stars are not going to do anything, aren't really contributing negligibly to this, because a star like the sun has a luminosity per mass of 1, so you're going to need a lot of much more massive stars for that to work in. So that's the radiation pressure force, and you can then rewrite this stellar mass in terms of the star formation efficiency times the original cloud mass. What about the gravitational force that you're fighting against? You can write that in terms of there's some material that is ejected. That's 1 minus the star formation efficiency times the original cloud mass. So then you can write that in terms of the mass per unit this is an m cloud over r squared. So if you equated these outward force and inward force, you would find that the efficiency has to exceed this value. And so that's what I wrote down a few slides ago. And it's basically increases with the cloud surface density. And of course, if you have a higher luminosity to mass ratio, that can give you a lower star formation efficiency. That's kind of intuitive. But the takeaway here is that at high cloud surface densities, you'd expect higher star formation efficiency. Okay, so what about from the ionized gas pressure? What does that do? Again, this is kind of what I wrote down before of the total pressure force from that ionized gas. The gravitational force is as written down before, and then you can see what is the requirement for the gas pressure force to exceed gravity. You can write it down like this. And what's this xi here is the ratio of ionizing photons to the mass of stars. Again, higher star formation efficiency at higher surface density primarily, although the cloud mass comes in here as well. So that's pretty idealized. H2 regions, first of all, are not completely spherical. But they're also not even necessarily embedded. That is, H2 regions, H2 regions are not always ionization bounded. Sometimes they're density bounded. That is, the ionizing photons can leave without actually interacting with the cloud. And then you can have, so this is kind of the schematic of that case here with what's called a blister H2 region. That is where the H2 region is essentially density bounded rather than ionization bounded. So you can think about this case and think about, well, now we're not totally enclosing this, so we're not actually losing any of the ionized gas. So we're not just pushing on the cloud, we're actually losing ionized gas, which is coming out in this, people refer to this as a champagne flow sometimes. So the gas is streaming away from this ionization front, which is typically it's a so-called critical front. So that means gas will stream away at about the sound speed of ionized gas, or about 10 kilometers a second. So if the density is this, then the total photoevaporation rate from the surface you can write in terms of whatever the density in this region is times that ionized gas sound speed times the area. But then this region is basically part of an H2 region, so you can still say that the density there in that ionized gas should scale in the usual way with the ionizing photon rate and the size of that H2 region. So that gives, if you put this in here, that gives you this photoevaporation rate. And that photoevaporation rate, it says, how fast do you expect to just photoevaporate gas and have it just stream away from the cloud at 10 or 20 kilometers a second? Of course, that will also have a back reaction on the cloud. And it turns out that if the back reaction is just this, the photoevaporation rate times the sound speed times the, particle mass. And that turns out to be just about the same as if you have an embedded H2 region and you look at what the force is applied. So you'll recognize this from the previous slide if you have it all in your head. Okay. So what do you get from the photoevaporation rate? Well, you can say if I use that photoevaporation rate, and how long would it take to lose, so within a freefall time, if I want to lose everything else in the cloud other than what I've turned into stars, what star formation efficiency do I need? And that's what's written here. Again, it increases with the surface density of the cloud. And there are different kind of solutions for this. This is from our recent solution, which we are comparing to numerical simulations. I'll show you that in a minute. But there are other previous solutions that say, in order to destroy the cloud, the H2 region has to propagate over a size scale comparable to the cloud. And in that case, you would get an efficiency that has this scaling with the cloud properties. Okay, but whatever kind of simple treatment you want to use, it does suggest that, again, there should be a higher star formation efficiencies for higher surface density clouds. Okay, so that's kind of to give you a framework for what H2 regions should do. But we're now at the stage when we don't, we can go beyond just these analytic models and actually do numerical simulations. So I'll show you. So this is from a numerical, let me pause it for a second. So this is from a numerical simulation where we're just including the non-ionizing radiation, so no ionizing photons, just non-ionizing radiation. This cloud is 50,000 solar masses, initial radius of 15 parsecs. So this is kind of a typical GMC in the Milky Way. And I'll show you, as I run the movie, you'll see the evolutionary effects from the radiation, which is applying a force to the gas. So this simulation uses the M1 two-moment method that Roman told you about in our implementation within Athena. So these are sync particles that represent clusters that are forming, or subclusters, and you can see that the gas is now being pushed away by the radiation force. The low-density gas is expelled faster and sooner, and over time, you can see that the higher density gas starts to be expelled away as well. So you can see that it takes time. One of the things that's pretty obvious is that the dense regions remain longer in the cloud. And that shouldn't surprise you for the reasons that I mentioned before. That is, higher star formation efficiency is required at higher surface density. So another way to think of that is you need a larger luminosity to expel higher surface density cloudlets within a given cloud. So if we think about a given cloudlet, what do we need in order to expel a cloudlet that has a given surface density? So you just match radiation force to the gravitational force holding that cloudlet in the cloud, and the requirement in order to expel it is you have to have the star formation efficiency has to be such that the so-called Eddington surface density is less than the surface density of that cloud. And you can write the Eddington surface density in terms of the star formation efficiency and that light to mass ratio. So if you treat the whole cloud as just, in this spherical limit, you get this dashed line here. That's, pretty low star formation efficiency, consistent with that analytic prediction. That would be about 3% for a cloud that has a surface density of 100. Each of these points here is from a numerical model. So that's showing that the actual star formation efficiency is much higher. So why is it much higher? Well, it's higher because you don't have just a given surface density. In fact, most of the material is in structures that are much higher surface density than the initial cloud was, because the turbulence has clumped up the gas, and at higher surface density, you need higher luminosity to expel it. So whereas you could have expelled a spherical shell at much lower luminosity, you actually have to keep converting gas into stars to get a luminosity high enough to expel the higher surface density structures in the cloud. So that's the turbulent model, where we basically say, what luminosity do you need to expel the structures of the highest surface density that you'd get for a given, for the log normal PDF that you get out of turbulence. So what about ionizing radiation? So there are also simulations of ionizing radiation, and this is from an earlier set of simulations by Dale. So similarly to the case for non-ionizing radiation, the fact that gas is clumped up in clumps and filaments means that it's harder for the radiation to affect most of the gas. And so what that means is that effectively the radiation is less effective than it would be if the material were completely uniform. And this shows the fraction of mass that is unbound at the time that supernovae would start to form as a function of cloud escape velocity. So in these simulations, they found that actually the net expulsion fraction, so the star formation efficiency would be 1 minus this. The star formation efficiency would be extremely high in clouds that have a high escape speed. Okay, so what if we include both ionizing and non-ionizing radiation? I'll show you now some simulations that use, instead of an M1 two-moment method, instead this is using the an implementation of adaptive ray tracing, which Roman mentioned as well. So this is a cloud which is similar to Orion in mass and size. Again, you'll see these sync particles, which are representing subclusters. Gas is being expelled. What's shown on the right here is the emission measure, so this is used in observations, but this is telling you this is a measure of how much gas is ionized. And you can notice, I'll play that again. You can notice that, first of all, you don't see any Stromgren sphere here, right? Any Stromgren sphere? So everything, there's a whole ionized region from the very beginning. There's much higher electron density right around the sources, but the whole cloud can be ionized relatively quickly because this turbulence creates a lot of structure, and the photons can make their way through all of those holes to ionize a lot of the interior of the cloud. Okay. So, So how do the forces compare to these idealized estimates of what the force is? That's what's shown here. So if you look, so the red here is the actual thermal pressure force compared to that analytic estimate that I gave you. And so you can see that it's maybe 10 or 20% of the analytic estimate for a given cloud size and ionizing photon rate. And in blue here is the radiation pressure forces compared to the analytic estimate, which is L over C. So you can see that turbulence actually, the fact that this is not a spherical cloud means that the effectiveness of the feedback is significantly reduced compared to these simple analytic estimates. And what are shown here are, this is, if I correct for the escape of photons, this is comparing the radiation force with, if I just take L over C, but I'm only including the photons that are actually trapped. I'm not including the ones that escape. So that you get closer here. And this is the gas pressure force if you're including the actual photoevaporation rate. Okay, so this shows the star formation efficiencies. The black stars here are including both ionizing and non-ionizing radiation. The blue squares are only non-ionizing, and the red squares are only ionizing. You can see that the ionizing radiation is more important than the non-ionizing in the sense that you get closer to the net efficiency with both if you are including only the ionizing. So the star formation efficiencies here are maybe about 10% or lower for low surface densities, but they get up to 50% for high surface densities. And over here, this is comparing an analytic model based on photoevaporation, so I don't think I have time for that. Okay, so how does this do in comparison to the observations? Well, the upper limits are actually reasonably similar. It's not clear exactly how to interpret the observations for the average, but it may be that if we take that average as something like half of the final star formation efficiency, this would say that if we're thinking only about H2 regions, you would have to have pretty low surface densities in order to have final star formation efficiencies of sort of several percent, because that is only down around, that's only down around here at very low surface densities. And GMCs don't seem to have surface densities that are that low. So how do we, what is the interpretation of this? Well, one interpretation is, of course, that's not the only form of feedback. And indeed, there are other forms of feedback, and one additional form of feedback is supernovae. So this is just showing a simulation that includes radiation, and then in addition includes the effects of one supernova. In fact, in this particular simulation, the cloud is still around after this after the supernova goes off, and you can kind of make an estimate of what you would need in order to destroy the whole cloud if you compare the momentum from that one supernova to what you would need to actually destroy the whole cloud, and you would need actually about 10 supernovae in this particular model. But more generally, there are supernovae not just in individual clouds, but there are supernovae from neighboring clouds. There are also runaway OB stars which can affect a cloud. So what I'm showing you here, Changgu showed some other results from yesterday. So this is from a simulation where we're looking from above at a patch of a galactic disk. This is surface density, and you're seeing the locations of individual star clusters that form in the simulation, and you can see them form in dense regions and then disperse that dense region. So, many supernovae form from the star clusters that are associated with those overdense regions. So it's important to include supernovae, but it's in the future, I think there will be more inclusion of supernovae in simulations of individual clouds. But you can see that you really should be thinking about this in a global environment, not just in a local environment. Of course, the local simulations give you higher resolution, and so you want to make sure that you're following everything correctly, and there's no substitute for higher resolution to do that. Okay, so I'll come I'll come back to that in a moment. To talk about thinking about the large scale pieces of a galaxy. But before I do that, let me say a little bit about extreme star formation. So I showed this to you previously, that in some regions there are clouds of much higher surface density and quite high mass, where actually the timescales are pretty short compared to when you would get a supernova. So in clouds like this, there's supernovae may never be able to may never occur within these individual clouds. And so in this kind of environment, what kind of feedback can there be? These also have higher escape speeds than from ionizing radiation. So another form of radiation that I haven't talked about yet that can affect the evolution is trapped infrared radiation. So for trapped infrared, since these clouds are in NGC 253, these are very opaque to even the infrared. So the total optical depth in the infrared, that's how many times infrared photons are reabsorbed. And from each of those reabsorptions, you get an additional kick. So the total radiation force, you get this extra factor to multiply what was originally just L over C. And there have been some suggestions that, in fact, IR radiation is the dominant feedback for the most extreme systems. However, one issue is that the radiation, can actually go around the material, not just push on material. And in fact, there does tend to be some anti-correlation between matter and radiation when you actually do detailed radiation hydro simulations. And this is showing the Eddington ratio actually tends to about 1. So that means the radiation and gas adjust where they are so that you get approximate force balance in the system. So these are simulations where they just put in by hand the luminosity and the gravity. So if you want to understand how this can determine the star formation efficiency, you have to do those self-consistently. So now I'm showing you, again, just the effects of infrared radiation. And this is similar to what I showed you before for the non-ionizing radiation only. But now this is infrared, and all of the radiation that's absorbed is locally re-emitted, rather than the radiation that's absorbed just goes away. And you can see that the cloud can be expelled by the radiation force. So this is for a particular choice of the opacity. You can do these simulations for different values of that opacity, and here's the result of that. So these are plots as a function of time, of the star formation efficiency the remaining mass and gas and the mass that's ejected. So these are all low opacities. Opacities of, this is 1, 5, and 10. This is opacity 20, 30, and 40. So at low opacity, most of the material is turned into stars. At high opacity, you can see that there's a real distinction between, this is kind of a bimodal effect of high opacity, the star formation is limited, low opacity, everything ends up turning into stars. So how can you understand that? Well, let's just go back to the simplified idea of just looking at a little piece of a shell. In this shell, there's a total optical depth. And so there's a radiation force on that shell, which is the optical depth times the luminosity over c. There's also an inward gravitational force, which you can write that like that. So what you need to push that shell or a little piece of cloud out of the system, you need to have the radiation force exceeding the gravitational force. But notice now that actually this has no cloud properties in it. This only depends on the opacity, which is basically a property of the dust, and the luminosity to mass ratio of the, which is sampling the IMF. So there's nothing here about the cloud properties other than the dust properties. And as you get to, a higher luminosity to mass ratio, you could disrupt, or a higher opacity you could disrupt. That means that if you take the standard value for kind of Krupa IMF, the critical opacity would be 15 in order to have disruption. And that is just right here between, the cases that get disrupted down here and the cases that essentially have star formation efficiency going to unity. So these are super Eddington radiation. These are sub Eddington. So there is this critical opacity. How does this opacity compare to actual values of the opacity? Turns out that the actual value of the opacity is probably not large enough for IR radiation to be significantly important, unless you're in a system that either has is dust enhanced or has a higher light to mass ratio than for Krupa IMF. For example, so if there's a top-heavy IMF or if the dust is enhanced, then you could get above this the critical value in order for IR radiation to be important. So that is probably part of why the star formation efficiencies in these clouds appears to be so high, because the collapse time is so short, and so that supernovae can't be affecting them. The gas pressure forces are relatively very small because the escape speed is so large, and because unless they're quite dust enhanced, or if they had there was a very top heavy IMF, the IR radiation is not all that important either. Okay, so let me turn now to large scale regulation of star formation. So here are the again the Kennicutt-Schmidt type relations, which show star formation rate as a function of gas surface density. But actually, gas surface density is not the only thing that matters. So this is, again, star formation rate as a function of gas surface density. But it's also, the star formation rate also increases with stellar density. So this is a little bit more like the star forming main sequence of galaxies, that star formation rate actually increases with the stellar content. But here, this is resolved. This is not integrated over whole galaxies. So it's saying that not only the fuel, that's what's here, but also the environment are both kind of equally important. If you look at the correlation, they're kind of comparable, whether you look at the correlation with gas or the correlation with stars. And this is something that was previously noted by others before. This is showing the essentially 1 over the depletion time, or the star formation rate per unit gas mass. This is increasing with gas pressure, and that gas pressure depends on both the gas surface density and the gravity of stars. So let's return now to this concept of self-regulation. And it turns out that on large scales, you can actually predict what the star formation rate has to be in order to have a kind of completely self-regulated system that is in which you're balancing gains with losses and you're balancing forces for the overall system. So I'll talk about how that works. But first, I have to say a little bit more about supernovae, because supernovae are actually the most important feedback in terms of the force balance, which you can also think of in terms of the pressure gradients. Okay, so Ramon talked about supernova remnant or blast wave expansion, and I also talked about this previously. Supernova remnant expands for uniform medium. It cools when it reaches and a shell forms when the size gets to a few tens of parsecs, depending on what the density is. After some tens of kiloyears, you'll notice that the shell formation is really quite well characterized by when the velocity reaches a certain value of about 200 kilometers a second. This is very insensitive to the density. So why is that? That's because at that shock velocity, the post-shock temperature is just in the range that you get very strong cooling. So that's essentially what determines when a supernova remnant cools, which is when is the post-shock temperature right inside, in this dense region, right inside the shock. When is that, ideal for radiation? So these are for a uniform medium, but of course the ISM isn't uniform. So this is showing a simulation of expansion of a single supernova remnant in a cloudy ISM. It turns out that the shell formation time is pretty close to what it would be if you use the intercloud medium here. If you also look at how much mass there is, let me show you this. This is showing from a set of simulations from Chenggu's work this shows mass as a function of time. So this is the hot gas mass, and that's the warm gas mass. So the hot gas mass reaches a maximum at shell formation time, which is still about 1,000 solar masses. This shows momentum as a function of time, and you can see that again, the material is accelerated, but it reaches a maximum value of the momentum basically when cooling is complete and there's no more strong pressure force making the material expand. And so the final momentum is actually quite similar to what you'd get in a uniform density case. And maybe that shouldn't be surprising, because in the uniform density case, notice there's a very weak dependence on density. So the fact that the density, that as density varies, we might not have expected it to be the final momentum injection to vary that much, and indeed that's the case. But you do notice that both the cold clouds as well as the warm intercloud medium all get accelerated in the expansion. So as I mentioned, supernovae are correlated, and this shows the result of an idealized superbubble expansion in a cloudy ISM for multiple supernovae. So in this case, there's a supernovae every 100,000 years, which would be the case for a cluster that has about 30,000 solar masses. And you can see that you get, again, this expanding hot gas, so it's hot in the center, and the material, whether it's cold material or warm material, is all pushed away from the center. So for superbubbles, as well as for individual supernova remnants, you can look at what the momentum is. And it turns out this shows momentum per supernova as a function of time or as a function of bubble size. And the relevant size here for superbubble is comparing to the scale height of a disk. And you can see that the range of this is for different simulations that have different supernova rate and different density. But you can see that these all have momentum pretty similar to the value for a single supernova remnant. And it's not too sensitive either to density or to supernova rate. So it's all about 10 to the 5 solar masses kilometers a second. Okay, so why have I told you so much about momentum? I told you so much about momentum because it's essential for driving turbulent pressure in the disk, and turbulent pressure is the main, the largest dominant pressure in the interstellar medium. So if you want to understand the interstellar medium, you have to understand how you have driven turbulent pressure from supernovae. So let's see how this works. So one way to ask how does the turbulent pressure depend on the star formation rate is to look at the balance of driving and dissipation of turbulence. So if you have a momentum input rate of p dot and the final velocity dispersion or final velocity when this reaches its largest scale of sigma, then that would be the energy input rate per unit mass. And you could rewrite that in terms of the, if we're looking at a little cube within the ISM, that's the momentum input rate per unit mass the momentum input rate you would get from the star formation rate divided by the number of all stars per high mass star and by this area. So that's the momentum input rate. Then the energy dissipation rate is just going to be how much mass there is times the velocity dispersion, and 1 over the crossing time, because the dissipation timescale is basically the crossing time. So just putting together all of the h's, you get this. So if you balance the input rate with the dissipation rate, you get turbulent pressure, which basically scales with the star formation rate and the momentum per mass. So you could think of that P star as that momentum per supernova, and M star is how many stars, total mass in stars per supernova, which is about 100 solar masses per supernova. So an alternate way to look at this is just to say, okay, I have a shell, and I'm just looking at the flux of momentum in the vertical direction, and that ends up giving you a factor of 1/4. Same scaling relationship, but it's kind of a particular geometry if you put your supernova at the midplane. So what this tells you is you expect the turbulent pressure to be proportional to the star formation rate per unit area with this factor, which depends on the momentum of supernovae and the mass per supernova. And that factor is about 1,000 kilometers a second if you put those two numbers together. So the other important thing that supernovae do is they inject hot gas. And this shows from the same superbubble simulations that the hot gas's asymptotic temperatures are in the range of 1 million to 10 million degrees. But after late times, there's really not that much hot gas mass left because, most of it cooled and made this accelerate in accelerating the shell. So the fraction of energy that's left is a small fraction of the energy that was put in, the energy left in hot gas. And the mass of hot gas is also only at most comparable to the total mass of stars per supernova. Okay, so I talked about the heating of the neutral ISM before, so I won't go through this in detail. But basically, from balancing heating with cooling, you get a thermal pressure which is proportional to the star formation rate because the heating rate from far UV is proportional to the star formation rate. And here, this yield coefficient is about 200 kilometers a second. So that's smaller than the yield coefficient for turbulent pressure. Not surprisingly, you'd expect that this to be somewhat smaller because indeed the thermal pressure is somewhat smaller than the turbulent pressure. And this shows from some simulations how the relationship between the measured thermal and turbulent pressures and these predicted pressures, if you use these estimates of what the heating rate is and what the turbulent injection rate is, using 1,000 kilometers a second there and 200 kilometers a second there. And you can see that these pressures are fairly close to what's expected. And this is averaging over long times in the simulation. So you can also look at the effects of magnetic fields. Magnetic fields, as Chang-Gu discussed, are created by dynamos in a turbulent shearing disk. So the dynamo amplifies any pre-existing magnetic field, which is probably very weak. So there's both a mean field that grows and a turbulent field. And of course, this turbulent field will reflect the velocity dispersion in the gas. And from simulations, we found, previous set of simulations, we found that it's about 40% of this. So that means that the turbulent magnetic pressure is similar to the other terms in the pressure in being related to the input star formation rate. Okay, so how does this compare with observations, this kind of expectation of feedback? How does that compare with observations? So this is looking at a set of the kingfish, so the Herschel Kingfish survey, which looks at the C plus 158 micron line. So that's sensitive to the thermal pressure in the cold atomic gas. And this is showing, actually, this is this is flipping it around the other way. That is star formation rate as a function of thermal pressure. And there you can see this linear relationship, which is consistent with the expectations of heating of the ISM by far UV. Let's see, yeah, I guess that's there. So this is, putting together this driving with dissipation and heating with cooling. We expect that feedback will actually set the pressure in the ISM. But can it really set the pressure? So it can set the pressure, but actually there's not, you don't have a choice of what the pressure should be because there's a weight of the ISM, and that weight of the ISM also says this is what the pressure has to be. So you're kind of saying, this is the pressure I can give you, but you also have gravity saying, this is the pressure you must give me. And that's what's shown here. That is, if you have a given gravitational field, and this is how much ISM you have, then there's a weight, which is how much, it's like the weight of our own atmosphere. There's a weight at the midplane just from holding up that atmosphere. And there's a term which is from the gas self-gravity, and then there's another term from the stellar gravity. So if you want to balance that force, you have to have a certain pressure. And that pressure is composed of a bunch of different terms that I discussed. What this is saying is that since these individual pressures are related to star formation individually in this way, the star formation has to, come to the table sufficiently to balance this gravity. So this is saying ISM force equilibrium actually demands a certain level of feedback. So this is just a reminder of what the Tigris simulations look like. Chang-Gu showed these to you before. So this is density, temperature, this is magnetic pressure, that's velocity, and I think that's gas pressure. So in these simulations, we can, and this is for a number of different parameters. So this is both outer disks where the weight of the ISM is very low, and inner disks where the weight of the ISM is very high. And you can see that the midplane pressure is actually very close to the time average weight of the ISM gas, where this is directly measured in the simulation. You can also use this approximate estimate of what the weight is, just based on what the gas surface density is, and an estimate of the gravitational field, and you can see that that also is quite consistent. So this is saying that indeed feedback is able to maintain and match this required pressure for equilibrium. And I can mention that these systems up here at very high surface density are actually not, very long-lived systems. These are they're actually very transitory, but still the time scale, the dynamical time is still quite short. So if you're averaging over the dynamical time, it still has to be in an approximate equilibrium. And this just, I think in the interest of time, I won't play this. This is just the different components of the pressure. So now, so that was, driving, balancing, dissipation. So putting that together, the star formation, now we can look at the star formation rate as a function of the total pressure, either the measured total pressure or this expected total pressure. And you can see that, again, it's consistent with expectations, where these expectations have two parts of it. One is the energy balance, and the other is essentially momentum balance. And this is showing from observations the relationship between star formation rate and total pressure. And this is consistent with what's shown here is the black curve from the previous set of simulations. And actually, that's what's shown here as well. So the new simulations that have more accurate ISM physics are actually quite consistent with those older simulations as well, where we really just included the momentum input from supernovae. We didn't have a hot ISM. Okay, so the basic takeaway here is that the ISM conditions and the star formation rate really have to be self-consistent. And there's a balance of energy gains and losses, and there's also a force balance. And what that implies is, people, you will hear all the time people say star formation is inefficient. But star formation is not inefficient if you actually look at what it gives you, not what you need to, So it's very efficient in terms of energy return because, nuclear energy processes are very efficient. So you're getting a lot of energy and momentum back for using up very little of the gas. So it's kind of a trade-off. You're getting something, but you're getting a lot for what you give. And this is kind of putting together the results comparing to starbursts up here and normal galaxies down here. This is basically the same as the Kingfish galaxies, but this is for starbursts. It's following the same relationship. And so I would argue this is a better way to look at star formation than in terms of the gas surface density, because it's both taking into account environment as well as the environment in particular of the gravity, as well as the fuel for star formation. Okay, so I think we don't have too much time, but I'll just say a word or two about galactic winds as well. Okay, so I talked about, in a sense, internal feedback and what internal feedback can do, but that's not the only effect of feedback, and we've heard that from Raman today, and we also heard that before from Ramil and Priya as well. So this is kind of a poster child of wind driving. Actually, though, I don't know if people know this. This is a very small galaxy. This is not a big galaxy. It's an extreme galaxy, but this is not like the Milky Way. So this is a very prominent starburst and a very powerful wind, but that it's actually easier to drive a wind from that than from some other things. Okay, so if we think about galaxies evolving over cosmic times, there's, how is star formation regulated over long time scales? Well, gas is coming in, but it also, in principle, can leave. And so there's some kind of balance between material entering and leaving and also being recycled kind of locally in the local even in the kind of fountain flow, which is a more local recycling, or the CGM, which is a somewhat more distant recycling. As Meow talked about, gas gets out to some tens of kiloparsecs before returning. So what are the feedback processes that regulate that? Well, to some extent, it may be the same things that regulate internal star formation. But the particular ones may be different in galaxies different galaxies. So, for example, in dwarf galaxies that have very shallow potential wells, photoionization and radiation pressure may matter because those are more like just individual giant molecular clouds if they're low enough mass and have shallow enough potential wells that photoionization may be effective for clearing those out. In dwarf galaxies, superbubbles can accelerate gas to moderate velocities, and then that material, the you may be able to clear out dwarf galaxies of warm and cold neutral gas just by acceleration in superbubbles. So for a massive galaxy where the potential well is deeper, hot gas can easily escape from even fairly massive galaxies. But as I'll talk about in a minute, you may not get that much hot gas unless the star formation is more extreme. And finally, cosmic rays may be important in ways that are less significant for regulating star formation within galaxies, basically because the spatial scales are larger, and this is something that Greg and his students have worked on. So if we really want to understand these processes, it's essential to have high-resolution simulations. And this is something that is a very active study right now. So here's a beautiful nearby galaxy, NGC 891. And you could think of the simulations, some of which Miao showed you and Chenggu showed you, as looking at a local patch within a galaxy, but you have high enough resolution that you can really follow the details of the feedback processes. So what are the challenges? Well, for hot disk winds, the big challenge is that generally the cooling radius, if you put the numbers in, the cooling radius is actually smaller than the disk scale height. That shouldn't be too surprising because the disk scale height is actually set by superbubbles. So you can't escape because you're just running into the material that got there from, that was pushed there from the last superbubble. So since gas tends to cool before it escapes from the galaxy, the amount that actually is available to escape is relatively small. And what's shown here, I think Chenggu showed you, is the mass loading. This is the hot gas mass loading. So it reaches, all of the hot gas is created in here, and then it's just basically flowing outward at, more than, it's supersonic, but it's flowing outward and not much is cooling, basically because what was going to cool has cooled already. So now the density is low enough that it doesn't cool and it can escape. So the difficulty of hot disk winds is that it's difficult to really put that much energy into them because the superbubbles tend to cool. Now, there are exceptions to that. One is if there's a starburst. So if there's a starburst, as particularly happens in something like M82 in the center, if the star formation rate is strongly enhanced over the previous star formation rate, then the superbubble will not cool at the time that it breaks out, and so it will still have a lot of hot gas in it. So if there's a very strong burst of star formation, that can actually lead to much more hot gas mass loss. Another possible exception is if the supernovae are fairly broadly distributed with respect to the ISM. And one uncertainty is actually what fraction of the stars are runaway stars. So that's something that's fairly uncertain. So one of the things that Miao looked at was how, depending on the distribution of supernovae, how the hot gas mass loading depends on that. Okay, so there are some difficulties of creating hot disk winds. I'll also just mention that there are numerical challenges as well. And so this is really why you want to do these very resolved simulations, because if you have low resolution, one thing that can happen, and this is even if you have, even if you have mesh refinement where you're saying, okay, I'm going to put a lot of refinement into the star-forming region where, most of the mass is, and I know I have to resolve the gravitational collapse. I'm not going to worry too much about refining the low-density material. But what can happen in that case is that you could have numerical mixing between the low-density hot gas and higher-density warm gas, which arrived there in a fountain flow, doesn't have, enough velocity to escape, but is spatially co-spatial with the hot medium. And this is just showing, what could happen in that case. So if you take so this is the velocity of hot gas in this simulation, and that's the velocity of warm gas. And if you just take the total fluxes of density, momentum, and energy, and you add the fluxes of those, and then you ask what's the velocity of the mixed medium. The velocity here would be, in the middle. And so depending on, what environment you're in, if you mixed hot gas with warm gas, this could either escape when it shouldn't escape, say in a dwarf galaxy, or, if you had hot gas, which could escape, but now this velocity is below the escape speed, then the metals that were in the hot gas would not be able to escape when they should escape. So mixing can give you unphysical results, and that's why you really want to be able to do high-resolution simulations to understand what a wind can produce, a multi-phase wind, because the different aspects of it carry different physics with it. And implications for galaxy formation and evolution. So before, I think I just say a word about outflows and fountains. And so that is that, as I mentioned, supernovae can accelerate warm gas to kind of moderate velocities of 50 to 100 kilometers a second. This is just showing at different heights of, at the midplane, you have basically a Gaussian, then you see this exponential tail in the velocities if you measure the mass as a function of velocity higher up, so a kiloparsec or more above the disk. So this material can escape from a dwarf galaxy, but for a galaxy like the Milky Way or 891, it will basically make a fountain because and so what this is showing is as you go to further away from the disk, there's less and less mass in this warm gas. So, there's relatively more here, but this is down by a few orders of magnitude. The high velocity tail is not that different because it had high enough velocity to get to that height. But the low velocity material basically reaches a maximum height and it falls back. And that's why the mass loading is decreasing as a function of distance from the midplane for the warm medium, because it basically reaches some height and drops out. And so this is, the mass flux is not conserved as a function of height. But potentially this can be, the velocity as the mass as a function of velocity can be characterized, and then we can have kind of a subgrid model for warm winds from galaxies. And that's something that we are working on right now. So ask Chenggu about that for simulations in different environments. So finally, I'll just mention that a number of people have also been working on how cosmic ray pressure gradients can actually potentially pick up material that is in this fountain and carry it out of a galaxy. And under favorable conditions, you can get a mass loading which is kind of comparable to, which is of order unity in a Milky Way type galaxy. But this is something that, again, needs to be studied at high resolution with accurate methods for treating the cosmic ray fluid. Okay, so I'll just wrap up by saying there's a lot of recent progress in understanding feedback, particularly at small scales in understanding, GMC scales and scales of kind of patches of a galactic disk. We think that we can explain star formation rates pretty well when we're kind of averaging over a patch of a galactic disk. I think what we still, need significant work on throughout the community is understanding kind of the connection to the longer timescales and how winds are driven. There's still a lot to be understood there, and I think it's a great opportunity for all of you. Everything is not solved, so plenty for you to do. Okay, I'll stop here.
So Romin showed us the first day that the mass loading, if you want to reproduce the luminosity function, the mass loading has to be inversely proportional to the sigma of star formation rate. Mm-hmm. And you showed all the momentum depositions are actually proportional to the sigma star formation rate. So the fact that it has to invert, is that because there are different dominant mechanisms in different scales?
I
in
mean, I think it
galaxies?
has to do with the escape speed. So,
It's just only escape.
yeah, I mean, if that's the case, if it really works the way that it has to work and it's not fuzzy dark matter or something else, then it's a question of, so momentum is not just momentum, there's also a velocity, right?
Right.
And so that velocity, the potential well that you're in, it matters what that velocity is relative to the potential well that you're in.
So, are there any situations, maybe if you have a clumpy ISM with relatively small clumps, where the effects of the feedback, like the heating of the environment and maybe photo evaporation, could like completely dissolve those clumps and prevent them from otherwise forming stars?
Oh yeah, I mean that's basically what happens in. I won't try to page back to it, but in a GMC, with a low mass cloud that has ionizing radiation, basically it's almost entirely photo evaporated. So you can you can basically photo evaporate very, very effectively, because the cloud has a surface. These individual cloudlets have surfaces that you ionize from.
Yeah.
Turning red. I'll just speak up. So in the simulations you showed the sync particles. Right? The sync particles represent not individual stars, but like clusters or clumps or something like that, which sort of sets a minimum scale on how clustered the supernova are, I think. Is that a significant source of uncertainty? Or, if you could resolve even smaller, would it, and they ended up not all being in the same place, would that make much of a difference?
Well, so the point of comparison is going to be the shell formation radius compared to the correlation of stars. So the clustering scale is always going to be very small. So I think that this is an excellent point, though, is like how clustered are the stars at the point that they have supernovae. So that's actually very related to one of the project proposals I had, which is that early feedback can actually disperse the material somewhat, so that you don't necessarily have the next stage of star formation as close as you would without the early feedback. So that may, I don't think that it's so we've tested this with kind of doing the correlation in simple ways, and it doesn't make a huge effect, but it does make some effect.
Another question on the other side of the room over here.
At the beginning of your talk, you had said that the cosmic ray pressure gradients act over different heights. Can you please explain that?
So the cosmic ray scale height is more than a kiloparsec, whereas most of the ISM has only a few hundred parsec scale height. So the pressure gradient scale is what determines the scale that the forces are applied on. So that means that there's not a strong cosmic ray pressure gradient applied to most of the mass of the ISM, but the material in a fountain, which is up there at a kiloparsec, above the disk, is kind of ideally located to interact with the cosmic rays, because it's not too much material, so there's a chance to actually be able to, if the cosmic ray pressure gradient over that scale can actually effectively accelerate it. So actually isolating a smaller fraction of the ISM is quite useful from the point of view of being able to drive winds.
I was wondering if you could elaborate on how processes that inject metals into the ISM are modeled in the simulations.
So this current simulations is relatively simple. That is, generally the metals are just put in the same region as essentially a color variable, as the as the other as the energy from the supernova. So actually, that's something that Chenggu has a project with a student. I guess is he? I don't know if he's here today, but looking at metal, exactly the diffusion of metals.
You want last question? Yes.
Yeah, so coming back to cosmic rays, if I understand correctly, you say that they can help launching winds, but they won't be a kind of internal process for star formation regulation, because the scale height, as you said, is bigger. But aren't they produced in supernovae? So aren't they supposed to be in the ISM for a while before they leave?
Yes. So cosmic rays can also. It actually, in principle, can help to boost the momentum input a bit, because after the cooling of the supernova remnant, you still may have the cosmic rays confined for a little while before they start to stream away. That's somewhat subject to exactly how you treat the cosmic ray diffusion. So there are definitely sources of cosmic rays. Of course, the total, if I had taken some energy and I had put it in cosmic rays, then it wouldn't have been there in the gas pressure. So, what it can do in principle is it can extend the pressure driving to slightly longer time.
One last quick question. You okay?
Okay.
Good.
So if there's other questions, I'm around for lunch and the rest of the day.